Y'all ready for this?
Alright, give the intro.
Alright. Hey guys, Sean and Nick here, and today we'll be educating you on the differences between a wave that produces sound and the sound wave that is actually produced.
Yes,
Pretty
awesome stuff.
Yeah, sounds a little confusing at first, but we believe that with our superior educational abilities, Sean works at
Revolutionary
Kumon.
knowledge.
I mean, he's a tutor.
I teach
so-
kids, actually. I changed the future of America, so
Yeah.
show me some respect.
All right, so this is a pretty cool program here. We do apologize for the background. Doseri, shout out. I'd like to give credit to this beautiful program.
Actually,
Great for
Doseri,
educators.
He's a great guy.
I'd recommend it to any fellow educators. Mr. G taking out could make your class a little more interesting. Just saying.
Gosh.
Just kidding, G.
Drop the
Love
hammer
you,
there.
man. All right.
Oh, man.
All right. So
Sure,
we just got to see on this project. But starting off.
I mean, I'll take it.
All right.
All
All right, Sean. Here we go.
Okay. We're going to use a xylophone bar throughout as kind of an example to show you the differences between a wave that produces sound and the sound wave itself. So what Nick's drawing here is a transverse wave. And the transverse wave is the wave that travels up and down, kind of like a sine curve. And the transverse wave is important to remember because it is the wave that is actually being trapped in the bar when you strike a xylophone bar. And those three drawings that Nick are drawing there kind of represent the xylophone bars and the transverse wave in it in three different regions of pressure. So in that first region is a region of higher pressure, and it's the crest of the transverse wave. And when that crest of the transverse wave is created, it creates a region of higher pressure and creates compressions in the air, as Nick's drawing there, which is part of the longitudinal wave. And the longitudinal wave is the type of wave that is created in a sound wave. Right, so, and then that second picture is the region of normal pressure, or represented in the node of the transverse wave, as Nick's drawing there. And that's just the normal air pressure of wherever the xylophone bar is. And in that third picture is the region of lower pressure, or the trough of the transverse wave, which will create a rarefaction in the air, which will the areas of lower pressure in the longitudinal wave of the sound wave.
Right. So, the point to remember here is that this is the transverse wave, and it is the wave that is produced by the xylophone bar, the instrument, whatever instrument you're using, the drum, whatever. And this, the longitudinal wave, is the wave that is in
The air.
the air.
And that's the way that you're actually going to hear the sound.
Correct. So the big difference we see here is the difference in material, the difference between the bar and the air.
So what are some things that depend on the material, Nick?
Well, velocity depends on the material of the wave.
So you're telling me that if the sound wave travels through air and the transverse wave travels through the bar, they're going to be different velocities?
That's right, Sean.
Whoa, that's crazy.
Yeah. So, here we go. Velocity depends on material, and this explains why not necessarily the wave that produces the sound and the sound wave itself could have, and most likely would,
Have different velocities.
have different velocities.
Cool, that's some Khan Academy stuff right there.
Yeah, don't know what that word means, but yeah. So, because in air, we know the speed to be 344 meters per second.
Right, and in your any usual classroom setting, that's what it would be.
Right. So, something that is similar for both the wave that produces sound and the sound wave itself.
So the frequencies are probably different too, then, right?
Oh, Sean, that's where you're wrong.
What?
The frequencies, believe it or not, the frequency equals the frequency.
That is not possible.
Yeah,
I don't see it.
regardless.
Show me.
Regardless of,
that.
and we will prove that. We will
Okay.
prove this. Frequency is the same whether you're talking about the wave that's trapped in the instrument, the bar, whatever you've got, the drum, and the sound wave that is produced in the air, the longitudinal wave. the wave that eventually gets to your ear and you hear a sound.
While that might seem a bit crazy, we're going to draw some diagrams here in a second to show you exactly how that makes perfect sense. So we're going to go back to the pictures of the bar when it's struck and the areas of the different pressures. So when you strike a xylophone bar, a transverse wave is created, as we were talking about. And in this first picture, you'll see the crest of the transverse wave.
Apologize, let me catch up. There we go.
The crest of the transverse wave, right? In the second picture, you'll see the normal pressure. And in the third picture, you'll see the trough of the transverse wave. And we're going to show you, once again, what effect that has in the longitudinal wave of the sound wave. So in that first picture, the crest of the transverse wave will create more compressions in the air of the sound wave.
Right, greater air pressure.
Right.
And then the trough
will have a lower air pressure, therefore there will be the regions of lower pressure and less compressions in the longitudinal wave.
Right.
So one thing you guys can notice here is that the same amount of time it takes for the transverse wave to go from the crest to the trough is the same amount of time that it takes for the longitudinal wave to compress and decompress.
Right, to compress and rarefract as the technical term for it. So you can see that the frequencies are in fact the same, and the frequency, of course, is what you hear, Sean. What's the frequency?
Well, then that greater the frequency of the sound wave would be a higher pitch.
Higher pitch, right? So frequency and pitch are the same thing.
And now that you see that their frequencies are the same, logically that means the periods are the same as well.
Right.
Right.
All right, so we hope this gave you a little bit better understanding of the differences and similarities between the sound wave and the wave that produces the sound.
Right, so just as a summary, some of the differences are the types of waves, as the one in the bar is a transverse wave, and the one in the air is longitudinal and is the one that you hear. And also the velocities are different since they're traveling through different materials, like the air and the bar. But and the similarities between the two would be the frequency, with that demonstration that we just showed, and since the frequency is the same, their periods are therefore also the same. So we hope you enjoyed our presentation.
Yeah, and hope you get a little better understanding of this topic.
Yeah.
All right, thanks, guys.
Stay classy.